Alright, Rob here from Get Some Systems. We're going to continue on through this firmware. Sorry it's a little more confusing than I thought it would be. It's a lot longer to go through this than I thought it would be. Actually, it took a lot longer to do everything associated with this project. I've been working on these videos for like 2 weeks now, but I guess there is a lot more to this than I initially thought, but hopefully this all makes a lot of sense, and all these concepts you can kind of, if you're new to this, study up on. I'll try to come out with some simpler stuff, but these are all pretty much important concepts, and this is a good project that kind of puts them all together so you can see how an overall system works, and why all these little peripherals and all these little techniques are important, because they all kind of come together to help you solve a larger problem. So this video we're just finishing up, and we'll go over our main state machine algorithm where we kind of go through. This is a state machine that controls the overall thermal profile, our 140 to 170 to 215, and our hold times. And we'll also discuss this division routine because it is really handy. I'm glad I learned this because it will come in handy, and so hopefully this helps some other people too. And so I'd recommend kind of studying up on this like I did. I'll go over it quickly, but I'm not going to be able to explain this very well on a video here. You kind of need to just calculate some stuff out and write your own routine. But remember, we just finished up the ADC video, and effectively what we need to do is take this room temperature value and divide it by 10, and that'll give us our degrees C per digit. And so right now we have 10 digits or 10 samples per degree C, and so we need to divide by 10. And again, if you from the last video, you could divide by 5, but I picked 10, and then I kind of went through and wrote a bunch of code to do 10, and so I ended up just sticking with 10. But really you could do 5. I ended up doubling it. You know, you could leave this out, you don't have to double this, and just divide by 5. But so I divide by 10, I doubled it, so I get 10 samples per degree C from the room temperature, from the microchip temperature sensor, not from the thermocouple. Thermocouple is already taken care of because we picked our reference voltage to be such that we get a 2 millivolt per sample resolution, and that allows us, since we get 8 millivolts per degree C from the thermocouple, we can easily right shift by 2, which is division by 4, to get our 1 digit per 1 degree C, or 1 sample per degree C from our thermocouple. Alright, so get back on track so this video doesn't kind of continue on forever. The division routine, effectively with division, I need to divide by 10. So really what I need to do is multiply by 1 over 10. So to multiply by 1 over 10, you get the binary value of 1 over 10. Right? So I want to multiply my room temperature average right here. Remember this from the ADC10 ISR from the very bottom. That holds my 10 samples per degree C of room temperature after removing the 500 millivolt offset that we need to remove from the temperature sensor. So we need to divide this number by 10, and there's a pretty neat way to do this. What you do is you multiply it by 1 over 10, and if you find the binary decimal representation of 1 over 10, you're going to end up getting something like this. I just plugged this into a calculator on the internet. You're going to get 0.00011001100, and that just keeps going on. And what you do is you left shift this until you get a 1 to the right of the decimal point. So you want to left shift this till you get rid of all these zeros by the decimal point. You get a 1. So if you can see this on the screen, after you left shift this, you get 0.11001100. And we're going to do 8 bits. We're going to use 8 bits here. So you only need 8 of them. Now you take the most significant, well, really you have 9, because that kind of continues on, and you shift it till you get a 1 to the right of the decimal point. Then you actually truncate it to 9, and because of accuracy and rounding and math stuff, you use 9 bits, and then you add 1, and that gives you a little more accuracy. So what we did is we ended up doing 9 bits, and we added 1. So if you get 9 bits, you get, well, I guess you get that 1100110001. And so now you're going to add 1 to it and then truncate it to 8 bits, and so that's going to give you this, which is going to be 0.110011 1. Alright, so now that's the binary decimal number we're working with. So for this, what we do is really you just drop the decimal point, or you can say you shift it to the right 8, but really you just want this number, right? Because this number represents 1/10 left shifted 3 times. So remember that, because it's kind of, you need the left shifts too. The left shifts go along with this number. But if you multiply, what we're going to do is multiply our room temperature average by this number and its associated 3 left shifts. And so to do that, we can't really do that with a decimal. So what we're going to do is we're going to basically forget the decimal, which effectively is going to be 8 more left shifts. And so now we have a total of 8, 9, 10, 11 left shifts that we've done to this number. So we're going to take this number, 11001101, and we're going to multiply just this number, this integer, by our average room temperature, right? And then we're going to also tie these associated left shifts to it. And what we're going to do is multiply these two together and then shift it back out to the right that many places, and that will effectively be multiplying our room temperature by 1/10. Now, I guess if you haven't done this before, this part's kind of confusing too, but the way that we multiply, if you think of multiplication, it's really a summation of addition. So to multiply room temperature average, so to multiply 10 by 5, you can either add 5 to itself 10 times or add 10 to itself 5 times. So using that idea, we want to multiply our average room temperature, right, by this number, with which, if you remember to tie the correct number of shifts to make it back into a decimal, if we multiply these two and then shift, this multiplication and then the shifts will be the same as multiplying by 1/10. So first thing we need to do is multiply this number by this average room temperature. And so we do that by forming this loop. So this number, 11001101, in hex is CD. So that number corresponds to this in this loop. So in this for loop, we sum up room temperature this many times, and that's effectively multiplying room temperature by CD, or by 11001101. So after we get that, we go through this loop, which is effectively multiplication, and we pop out of here, and our offset temperature now holds the value of room temperature average times this binary number CD. And so now I saw somewhere for rounding accuracy add 1 to it, so I added 1 to it, and so I added one to that. And then now here's where we go back and apply our corresponding shifts. Remember, we shifted it to the left effectively 11 times, so now we shift it back to the right 11 times to get our decimal number. And so now we have effectively multiplied our average room temperature times 1/10. So our offset temperature is our room temperature, and that represents 1 degree C per 1 digit held in offset temperature. So our final temperature, which is what we want, which is a sum of the room temperature and the thermocouple temperature, now that both of these hold 1 digit per 1 degree C, we just add them together. So you could see down the ADC routine, I broke this average room temperature in half, sent it to the Python app, and had it divided by 10. But then I figured this out. So really, you could simplify this and just send this final temperature out. Or you can send the offset temperature, which is room temperature, or you can send the average temperature, which is the average thermocouple temperature. And then this flag just says go divide. It basically just tells this if statement, hey, enable, and when you're done with your division and you figured out the final total temperature, reset the flag, don't divide anymore until some other part of the program enables the flag and says divide these numbers. And so this while loop runs continuously, so it's either running through this code or it's running all the code in this main state machine, which we're about to go over, which hopefully will be pretty simple. But yeah, so, and I guess just to point out again real quick, remember down here, where is it? In these routines where my COM routines to send data and basically send data to the Python app, it doesn't send much back. See, I send room temp 1, room temp 2 for both of them. And basically you send a header and it keeps interrupting this until it steps through all these bytes, and then it clears the flag and interrupts again, but there's nothing to do, so you clear the flag and you're done. And remember, these are the same. You just send different headers. I just wrote 2 different code blocks here, so that if you send temperature data to be plotted, it does this one. You can kind of see them separate. If you send updates, it does this one and steps through these codes, and you can use the 2 temp variables. So it's 2 ways of solving the same problem. You can divide by 10. I divide by 10 in the MSP 430 with that routine above, or you can break the room temperature variable in half, send it across to the Python app. In the Python app, I recombine it and divide it by 10 there, because it's a lot easier to divide by 10 in the Python app. So that's that. I hope that makes sense. If it doesn't, Google it and read about it some more. All the comments are pretty detailed in this. I tried to write them as the best way I could and the simplest way I could to try to make it easy for everybody to understand this. So if you download my code, read through this, hopefully it makes even more sense reading through this and studying a little bit than just watching these videos, but or doing both at the same time or something. So our main state machine here, we switch on main state, and so this is a state variable that's initialized to 0 for our state machine. And so in the first case, in this while loop, we just continually check these 2 statements. So first we check this. If our flag's not set, we're not supposed to be dividing. We skip all that stuff. Then we come down here, switch main state. If our start thermal cycle flag isn't set, remember when we receive a 77 from the serial port, we set start thermal cycle to a 1. This kicks off our state machine. If that's not set, we break out of here and we don't do anything. We just sit here and spin and check these 2 things till one of them says go. So when you press run on the GUI, it sends a 77. The ISR for UCA 0RX receives that. We set our go flag. That kicks off the state machine. So the first thing we do is set our target temp to set temp 1. So this is our 140, where we're ramping up to 140. We set our thermal rate to 12,000. This is the maximum duty cycle. I think so. Yeah. Maximum duty cycle allowed for our PWM system. And if you look in functions, I won't go over this because I don't want to make this any more confusing than it is, but thermal rate here in increase, you can only increase CCR1, which the bigger CCR1 is, the bigger your duty cycle is, the wider your pulse is, the more time that the toaster is on, and the more time you allow the power to be delivered to the thermal elements in the toaster. That's what this is. So this limits the maximum value it can be, which effectively limits our ramp rate. You know, the smaller it is, the slower your ramp rate is going to be. The higher it is, the hotter they get, the more heat they'll put off faster, the more aggressive your ramp rate. But since we're only going up to 140, and I don't want to thermally shock the parts I've got in there for reflow, remember this is a real world application, so you know, yeah, you have to think about real world stuff. This isn't an academics thing, so it's a lot harder than what it would be in the academics world. You can't just go calculate something and assume it worked. But so our thermal rate set to a value of 12,000. So this gives us a pretty decent ramp rate, but not too fast to thermally shock any components. We set our state variable, go to the next state. We set our displacement. This is how much we add. Remember down here, every time we're supposed to increase our duty cycle because we're not heating up fast enough or we're not holding our temperature, this PWM displacement is what number we add to CCR1. So this controls how every time we add something, this controls how much wider our duty cycle gets, or the increments in which we step our duty cycle out to be greater and greater. And so the bigger this is, the fewer cycles it takes to get to 100% duty cycle. And then start thermal cycles reset. So to rerun this, you'd have to send another 77. But this is reset because we don't need it. We don't ever come back to this till we're done, I don't think. Or no, we don't ever come back to it. So we can clear our flag. It's good practice to clear your flags and know what's going on. So we're finally in case 1. This is our ramp state. We're going to ramp up to our temperature, and basically what we do here is we check to see if our final temp, which remember is the sum of the thermocouple and room temperature to give us our total temperature in degrees C. We check to see if the temperature in the toaster, which is represented by final temp, is equal to set temperature 1. So that would be, in our case, 140. So for a while it's not going to be. It takes about 60 seconds or so to ramp up to 140, maybe 80 seconds. So if it's not equal to this, we're going to go down here and just set our state variable to this same state. So if it's not equal, we're going to sit here and wait. Because remember, the whole time we're sitting there and waiting, the algorithm in our timer A0, CCR0 register is ramping up our temperature, and then it's going to be holding it. So we're letting this routine do everything for us. We don't have to do anything. All we do is set our target temperature to any number or any defined number, like here our set temp's 140. So we're basically just saying target temp equals 140, and then until here we're saying until our target temp reaches 140, don't do anything, just wait. And that algorithm in CCR0 takes care of everything for us. Once we get to 140, we're going to want to go to the next state. We're going to clear our main state seconds. Remember, this is a variable which is just a seconds counter right here. This interrupt, we execute this code every second, and so what I do is I append 1 to I add 1 to this variable every time this interrupts. So what effectively happens is when you clear it, you are starting a little stopwatch. So what I do is I clear it, it's set to 0, and it's going to increment every seconds, and then we change our displacement from 200 to 1000, because what we're going to do is set an even higher temp, 170. And so what we want to do is increase the duty cycle faster to help get up to that temperature faster. It's going to take more power, and we also want to increase the maximum duty cycle as well, but we'll do that in a minute. So we set some basic variables. Go to the next state, reset our seconds, which is effectively resetting a stopwatch that we use in the next state, and changing our displacement from 200 to 1000. So every time we execute increased duty cycle, we increase it by 1000 instead of 200. So next we go to the next state, and here we check to see if main state seconds equals 45 seconds. So remember, we just reset this to 0, and now we just sit here. If it's not, we stay in the state when we just sit and spin. And what we're doing is we're waiting 45 seconds, and this is how we get our 45-second hold time. And the great thing about this is all we have to do from the main program kind of point of view is just sit and wait. The algorithm in CCR0 is going to hold our temperature for us without any problems, as you've seen in the demonstration. And so when we wait 45 seconds, our window expires. We're going to go to the next state, and the next state is to ramp up to 170. So what we want to do is change our target temp here to 170, which is set temp 2. It's defined in our include file, 170. And we're also going to increase our thermal rate. So the max duty cycle now goes from 12,000 to 18,000. So that means we're going to deliver a little bit more power, and we're going to get up to the max duty cycle faster. So now on the next state, this is our second ramp stage to target temperature 2, and it's the same as before. If we're not at our target temperature yet, or basically below 170, we're going to sit in this state and wait. And we're going to let the algorithm in our CCR0 interrupt service routine handle all this for us. It's going to handle the ramp up to 170, and then we'll see once we get to 170, because we're monitoring the real-time temperature as equal to a defined temperature, a constant definition. Once we get there, we're going to go to the next state and reset our stopwatch, because remember, once we get to 170, we want to hold. So we reset main state, and then we come down here and wait. And this is the same stopwatch idea. We wait here. If 45 seconds, the 45-second window hasn't expired, we just sit in this state and wait. Once it has expired, we go to the next state. So we change our state variable to state 5, set our new target temp, which is 215, because we've reached 170 and waited for our defined hold time. So we're done with 170. So we set our new temperature, and we increase our thermal rate to 25,000. So this allows us to have 100% duty cycle, basically giving all of our power to the toaster without turning off. It's completely on the whole time. This is because we need as much power as we can to ramp up and hold in the 210, 220 degrees C range. So our hold time window expired. We go to the next state. We've set our new temperature and we've set our new thermal rate, which is our maximum duty cycle. Down here we do the same thing. We just wait till we get to 215. If we're not at 215 degrees C, we stay in state 5. We don't go to the next state, and we just sit here and wait and let our algorithm, again in CCR0, handle all of the thermal stuff for us, all of the duty cycle stuff, and that algorithm will basically ramp us up to 215 and then hold at 215 all on its own. And all we have to do is wait. When we ramp up to 215 and we see that, we then have our main state machine go into a 60-second hold. And this whole time, our algorithm in CCR0 is running all on its own to reach 215 and then hold there as accurately as it can. We don't need to fiddle with that at all. All we need to do is set a target temp and set what our maximum duty cycle can be and set what our duty cycle displacement, or how much we add to CCR1 for timer 1 to increase our duty cycle. The increments in which we increase our pulse width for our solid state relay. So we ramp up. Once we hit 215, we see that we've met 215, we go to the next state. We reset our stopwatch because we want to wait 60 seconds, and we change our PWM displacement to 2000. And we changed it to 2000 because this allows us to pulse width modulate up and down a little bit more accurately, because we don't want to turn the toaster off right away, and we don't want to turn it on right away either. So we get down to this state, our main state seconds is reset, so we got to wait 60 counts, which is equivalent to 60 seconds, so that's our 60-second hold time. And so until we've reached that, we sit here just like we have in all the other hold time states. Once we reach it, we change state. We set our target temp to temp 3, which really doesn't do anything. Basically keep our target temp at our final target temp. So effectively, I guess you don't really need this, but I wanted to just reset this while I was developing. But either way, our window expires, we go to the next state, and the next state shuts down our system. This shuts down our PWM functionality and our pin, and it sets the pin output to a manual 0. And there's no way to get out of this unless you reset the system. I like this because if you don't pay attention and it keeps running, it'll stay here off, which is good. You don't want it, heating up as much as it can, kind of getting out of control. So that's it. I know this is probably like trying to drink out of a fire hose, but that's the whole program. This is the main state machine, and this is the temperature control algorithm. And the reason I developed it like this is because I wanted to be able to set a temperature more abstractly and just let a interrupt service routine ramp up and hold automatically. So all I have to do is step through a state machine that consists of setting a target temp, waiting. Once it gets there, I can specify a hold time. If I don't want to, I can set a new temp, target temperature, and all I have to do is wait. Then I can specify a hold time. I can do this as much as I want. So you can keep tacking on states to set all kinds of temperatures. You can even tack on states to set temperatures so that you actually hold, you can ramp up and then go back down and hold. You could have a profile like ramp to 140, then to 170, then to 215, then down to 185, then down to 135, then down to 60, then back up to 120, and all you do is keep adding on states to this state machine, and this algorithm down here would handle it all for you. So I know that was fast, but that's the general idea. It'd take me forever to go through this in detail, just this firmware, and I've got 3 or 4 more videos to make on 3 or 4 more sections of this project. But this is by far the hardest one. I hope this helps, and I hope you found it interesting. I'm going to try to get the rest of this stuff finished up and get this project online. Thanks.